All right. Hello, everyone. Welcome to the Neural Dataset Competition Awards Ceremony and Tactics. Really excited here to share the tactics and the great work that our competition participants have been doing for the past about a quarter. Yeah. So let's dive right in. So this competition was run by two orgs, Neurotech at UCSD and DS3, and we'll just talk a little bit about our clubs first. So Neurotech at UCSD is affiliated with Neurotech X, which is an international organization that has chapters around the world. Our club here at UCSD was started in January 2020, and our faculty advisor is Vikash Gilja from the EC department, and we have connections with wearable sensing and participate in the annual student competition. And our club's mission is to bring together students who are interested in neurotechnology to provide a way to get involved in the field. So this is a great way to do that, and really excited to be here.
Hey everyone, my name is Tanvir. I'm the Machine Learning Workshops lead for DS3, which stands for Data Science in Society, if you didn't know. So we're basically an org that basically provides like a space or a community for people studying data science. You don't have to be in the major, or you could be in the major, but basically we provide. Sorry, what was that? Okay. Basically, we provide all sorts of resources for those people studying data science on campus. So we provide workshops, professional networking events, and also other sorts of events such as hackathons, and also this Kaggle competition for and projects for you guys to show off your skills. So if you guys are interested in that sort of stuff, then please make sure to check us out on social media.
Great, so we'll just go over a couple things today, just a summary about the competition, and then go through award ceremony and tactics. So just as a refresher, the Data Kaggle competition had about $200 in gift card prizes, and it lasted through week 3 of this quarter. And the goal was to predict whether or not someone was thinking to move their right or left hand. And this data set was based on a BCI competition from a long time ago. And so this is sort of the links that we had for the competition. We had some notebooks that had workshops that went along with it, and also a Discord for live updates and finding pairs and things like that. Okay, so just to dive right in, we're gonna go with the best neuroscience-backed methods for feature extraction. This award goes to Eric and Wilson. Hooray!
Thank you.
And they got $50. So yeah, they're gonna give us a little bit of a preview into what they did, and we're gonna celebrate. So take it away.
So for our group, Eric and I achieved an accuracy score around 82% in the final submission, which was 30% higher than our public leaderboard score. The picture of data frame here is the original data given by the competition. At first, we decided to delete the column of start time because we believed that it was kind of useless in our model. And then we separated the event type as predicting outputs and left the rest of the data as the features. Since each cell for each feature contained a list of 1,000 elements, we needed to find a way to aggregate these values or flatten them into 1,000 different cells. And Eric is going to talk about our feature methodology in the next slide.
Thanks, Wilson. Our first feature extraction method was transforming the aggregated features into individual ones. This is because scikit-learn's machine learning models work best with individual data. So we decided to explode the list features into individual features by designating each individual element as its own feature. So this resulted in a new data frame with 6,000 columns instead of our initial data frame with only 6 columns. And then our next step was deciding on a machine learning model for our pipeline. We tested different classifiers that we felt were applicable to this data set, such as naive Bayes and linear SVM due to the high dimensionality. And we used scikit-learn's grid search CV function to hypertune each model and ensure that we tested the optimal parameters. However, we weren't particularly well versed with this grid search function, so it definitely still has potential for improvement. And lastly, we wanted to continue engineering additional features, but we ended up running out of time. We only calculated simple computations, for example, like the range of CZ elements or the difference in max values of C4. But the addition of these features actually resulted in a lower accuracy than our baseline model. But with more time, we could identify more key features that would increase our predictions accuracy. And also a huge thanks to NeurotechX and DS3 for hosting this competition. Thank you.
Thank you. Awesome. That was really awesome to hear about. And we have prepared a awesome little certificate for you. Yes, you can, I guess, take a screenshot or something. We'll also have the slides for you. So congratulations. All right. Next up, we have the best data science and machine learning method goes to Anjuman, and he also gets $50. So this is what he wants to say about it.
Hello, everyone. Yeah, my name is Anjuman. I'm a first-year CSE master student. The title of my presentation is called How Not to Do Machine Learning. And I'll walk through the methods that I used and some learnings for myself as well as you all to share. So I'll share my screen. Or Jiling, do you mind turning off your screen sharing? So just for some background, I've never worked with the EEG data before this competition, but I am familiar with a variety of different machine learning methods. So instead of actually doing the feature engineering like the NeurotechX Club wanted us to do, I was like, hey, I could probably do better than this. Let me just throw all the data in a machine learning model and see what happens, right? But that's exactly what you're not supposed to do. And so I went through a variety of methods. As you can see here, it's like 7+ methods for analyzing the data, and they're almost all of them failed. So let me walk through kind of the different methods that I tried, and then hopefully you guys don't make the same mistakes that I do when first approaching this competition. I will highlight the times where I felt like there were some small successes. So I'll initially start by saying I started this competition by doing a bit of literature review, looking at how people have analyzed EEG data and specifically this competition data set before. And there are a few interesting papers that arose. So one was a paper by Google X and DeepMind that I was quite interested in, which used a beta variational autoencoder. It's a type of deep learning neural net that was able to do a good amount of dimensionality reduction while maintaining some interpretability of the data. And Google used this for their EEG headset prototype that they're coming up with, and I thought that was a cool idea. Another one that I saw was RFNet, which uses something called like Riemannian-based approaches. These are pretty simple approaches where it just use like derivatives of the EEG waveforms or distances in relation to the EEG waveforms to achieve pretty high accuracy. And then thirdly, I saw something called Esophagus, which was used some interesting algorithm, hard-coded algorithm for this. And one learning from that paper was that they actually created a model independently for each of the participants. So that was something that I wanted to try as well. So let me quickly walk through kind of the whole process that I took, and again, highlighting what worked and didn't work. So first, I tried data augmentation. So this is generating new data by adding some random Gaussian noise and seeing if that increases accuracy. I see Michael laughing a lot, and the funny thing is this is the one thing that actually did work. It did add 1% accuracy, so that was great. And then I tried a variety of sklearn machine learning models. They all failed. I tried a neural net, which was the one that I submitted at the end, and a convolutional neural net. And thank you DSP for some of the starter code for this. I tried transfer learning, where I've heard that like, hey, you could just take an image-based neural net like ResNet and apply that to EEG data, and it totally works. That's what someone told me. So I did exactly that, and it failed really miserably. Don't try that. I tried an autoencoder. So I thought like, hey, a beta variational autoencoder, that seems really complicated. I don't know what that is, but an autoencoder, I know what that is. So let me try using an autoencoder. That also failed miserably. I tried some Riemannian approaches. And so again, Blackbox took a package from the NeurotechX website, and I applied a few different methods that they had starter code for. And that failed pretty miserably as well. And then lastly, I thought, okay, maybe if all these models fail with all the data together, I should create a model for each participant independently and then aggregate the results, right? And so it was interesting for some of the participants, like participant 1, that was performing poorly with the aggregated results. This actually did come up with good accuracy just for particular participants. But then ensembling the methods and kind of averaging the results also did not result in a very high accuracy. So lots of failure. Here, I'll just quickly scroll through. If anybody would like to use this code in the future, go for it. It's a great starter code for implementing any of these models. I did use Grid Search CV, and I have this class that I create that kind of helps quickly test a variety of hyperparameters. I do this, usual train validation test splitting. Try a whole bunch of different sklearn models here, and you can see, like 70% accuracy, 68. I think it just gets words from there. The neural net model over here, and I noticed some overfitting, so I added some dropout because I heard, hey, dropout helps it with overfitting, and it actually did help with like 0.5% or something. Oh, that doesn't look too good. It's maybe without the data augmentation or something. Here's some code for the convolutional neural net transfer learning going on over here. Here's the autoencoder, which basically uses the training data as the target data that you're trying to predict. So it's basically trying to find lower dimensional versions of the data. And then the Pi-Riemann models over here. And then lastly, trying to create independent models for each participant. Yeah, and then I think the last thing that I did was I ran quick PCA with logistic regression, and that did fairly well as well. PCA plus logistic regression. And so I ended up submitting both the neural net and the PCA with logistic regression, and got like 78% accuracy or something. So something respectable, but bottom line, going back to the slide that I created, bottom line, this is how you don't do machine learning. You should try to incorporate some subject knowledge into your approaches. You should understand the models that you're developing. I mean, it's cool to fail fast, but make sure that your model and you are learning in the process. So yeah, thank you. Thank you to NeurotechX for the competition, and looking forward to, thank you to my fellow participants. It was a great previous talk, and looking forward to the winning talk after me. I think that's the right way to go.
Yeah, thank you so much. So do you want to also put up the slides again? Yeah. So yeah, for that, we'd like to, of course, award you the best data science ML methods for this competition. You definitely put a lot of effort into, testing out many different machine learning methods, which was really, really fascinating to read through. So thank you. Also hope you participate next year as well. So congratulations. All right, then we can also move on to our last winner, Michael, who created the most accurate model on our Kaggle leaderboard, public and private.
Yeah, I first want to shout out to Anjuman because I totally went through all the struggles you did. I'll address it later in my slide, but Yes, and we can move on. I'll start going over the method I use for the competition. So this slide might look a little bit compact and has a lot of information. It is because this is the part that I spend most of my time researching on. And so I would say this is probably, if you can integrate this part of EEG research into your own perspective models, you will significantly improve your models of performance. So the common question that Ashman was talking about is, why don't we just fit in the raw EEG data? Why don't we just, try out different model and just see if the model can perform well on the raw data? But it turns out that there's a really big caveat of doing that approach. The thing is with EEG data, because of the headset quality, as well as like the skull intervention when like the data is emitting to the headset, there's a lot of noise in the data that machine learning might not be equipped enough to filter those noise. I mean, one thing to combat that might be you can develop a really deep neural network or convolutional neural network that can kind of pre-process the data in the layers of the machine learning model. And some of those model might be like EGNet, like on the MNE library, which I steer away from using it because I'm afraid that my result will be disqualified if I use theirs. But you should totally try out their model if you want to perhaps jumpstart or elevate the accuracy of your model. So now let's talk about, now we know how important it is to filter the EEG signals. The question comes to us, how do we filter them? So, since this is my first time working with EEG data as well, I look at the research at the bottom of the slide, which is an improved discriminatory filter bank selection approach for EEG signal classification using mutual information by Xu, Alog, and Tashuko. So here, what you see, the visual on the slide is my version of it, but integrated with their version. So let me first walk you through what they do first. So if you look at the sub-band filtering section, you can see there's sub-band from 4 to 8 hertz, 6 to 10 hertz, to 8 to 30 hertz. And most people for their application, they probably just take the 8 to 30 band hertz because it has been proven in many studies that 8 to 30 hertz is really good at capturing most of the wave like mu wave, alpha wave, and other kind of wave. So if you just want to filter your EEG data, you can simply pick this one, 8 to 30 hertz. But in the research paper proposed by Xu and Alok and Tashuko is that instead of taking 8 to 30 as a default, they want to try out all different frequency band at the interval of 4 hertz to figure out the best subband. And how do they figure it out? They use something called the mutual information, which I will discuss in a little bit. And they use mutual information to quantify the best subband related to the output. And that's pretty much what they do. So they pretty much, and okay, yeah, that's what they do. Now I'm going to talk about what I did different from their approach. So if you look at the assorted filtering session, so in the research paper, the only kind of filter they use is the FIR filter. And instead of just using the FIR filter, I actually try out a variety of filter like instantaneous amplitude, PSD, lag coherence, and M by time, frequency by time, and so on. And for each of the single filter, I pass them through all different subband filtering. And all of them will be passed through CSP to reduce the dimensionality to be in order to pass to mutual information. And what mutual information does is it calculate the correlation of the feature to the output. So the one with the high MI score means that the feature is very highly correlated to the output. So the one with the highest MI score should be the feature that we want to use for the data. So after running through this entire pipeline, I figured out that the instantaneous amplitude is the better filter than the FIR filter. And the best frequency band for it will be covered in the next few slides. Finally, I use PCA to reduce the dimensionality of the data. Okay, we can move on to the next slide. There's a question, would this mutual information be similar to attention in deep learning? So I don't actually know what attention is, but I know mutual information is widely used in machine learning to select prominent or good features for the machine learning model. It's not only using EEG application, it's using other application as well. So this slide, if you look at the graph on the right, this is the mutual information score for each of the filter, the top 4 mutual information score. So if you see for the filter, the best frequency band or the best subband for it is from 26 Hertz to 30 Hertz with the MI score of 0.034. And its second best subband is from 24 to 28 Hertz with the MI score from 0.029. So here I want to put a spotlight on the AMP filter, the AMP by time filter. If you look at it, so if you look at the 5th column, you can see that the AMP filter has the highest MI score in every single row. So yeah, so from like the row 0 to row 3, the AMP filter has the highest MI score in all of the different row compared to other filters. And this corresponds to its performance on the DNN, which is the visual on the left. This is the learning curve from 0 epoch to 50 epochs for the performance of just EEG and EOG together on the testing data. And you can see the AMP filter with the highest MI score perform, like you can just see the trend that the AMP filters like beat all other filters by a large portion. So that's why that kind of give us a sanity check that MI score actually can give us a quantified result to see which feature is the best to use. And that's all for feature filtering and feature selection. And now we will come to how to retrain our model. And this is the nightmare. So yeah, I like Anjuman. I wasted like tons of time just trying to tune the hyperparameters. Like I probably spent like 2-3 hours trying to, adjust the layers of my DNN, adjust the layer of my CNN, change the number of neurons, add different kind of 2D conf, 3D conf layers, and just to find my accuracy to improve by like 0.7% or 1%. And I kind of just feel so frustrated. And yeah, so the hyperparameter tuning, in my opinion, is not that important as in feature selection. Anyway, so I went through training, I do some hyperparameter tuning. And for hyperparameter tuning, I also use like repeated careful cross validation instead of just k-fold cross-validation. And that's one of the advice I have for you guys, because I repeated k-fold validation has better consistency than just using straight up research CV. Like you should run the research CV multiple times to get the most consistent and best representative result. And for model selection, I simply look at the graph of the accuracy of each model on the test set, and the one like surpassing the accuracy of 75%, I keep them. Below 75%, I don't use them. And lastly, stacking. So stacking is the ensemble technique that Anjuman is talking about. But ensemble can actually be a little bit tricky. So what Anjuman was talking about is what is called the voting ensemble. So voting ensemble, you pretty much just take the output of every single machine learning model and you average them. And this, for me or for you guys, you can just realize how it's not really intuitive, because let's say one of the model just performed really bad, then you kind of lower the average of all the other models. However, with stacking, we have an extra logistic regressor or extra machine learning model that learns how this different model can work together to create the final output. So it's not simply just averaging the result, it's to have trained another separate model, then learn how this model can work together to achieve the best output. And that's the gist of Ensemble Model. And one thing you can see is like DNN, I put a dashed line instead of a solid line. There's just one caveat for you guys. If you try to use Ensemble Model by sklearn library, like it's not compatible with Keras model. So you just wasted all your time tuning like Keras model and try to ensemble it. It doesn't work. Like I spent like over 5 hours on it because I spent so much time tuning my DNN, but can I use it? So, but anyway, just something you guys shouldn't do. How to not do machine learning. So as you can see on the graph on the left, stacking has, so this is like the box plot of the accuracy of how the model perform. And you can see that stacking performs significantly better than any of the models that's being combined. So that's why we use the stacking model. And the graph on the right is just my desperate attempt to have my DNN be part of the stack model. So you can see DNN as stacked, and DNN as stacked still does not perform better than stacked because like it doesn't, like, sklearn doesn't provide an ensemble model for DNN. So I tried to manually create one on myself. It didn't work. It just kind of hurt losing the LeBron James on my team. Because if you look at the graph on the left, DNN is like the second best model in my collection. But it's okay. Life goes on. And yeah, that's it for my training. Okay, I'm sorry I took so long, but it's okay. We finally come to our last slide. So overall, like on the private Kaggle's data set, my model achieved the overall 89% F1 score. I believe we can surpass 90 if DNN was part of the stacking, but that's for my grandson to do. And one thing I have for you guys is that you should really do research on the EEG data instead of doing research on the machine learning model, because even with stacking model, it improved my model accuracy by at most 3 to 5%. But by selecting the right subband and by using the right filter, it improved my model performance by, I would say, about 8 even to 10%. Really do research on like understanding the subject you're dealing with first. Then you go to the machine learning model and you try to tune them. That will really significantly save you a lot of time. And along the line of saving time, you should, just use Colab and run their free GPU. Because if you try to run like research CV on your local machine, and use like n job equal to -1, pretty much your CPU is idle. Like you cannot do anything else like on your computer while you're training. And the training might sometimes take 10, even 12, 24 hours. So by running on Colab, like everything is run in the cloud. So it has nothing to do with your local GPU. So you can train your machine learning model while working on your homework or watching YouTube videos. And if you look at another technique is like dimensionality reduction. So the original dimensionality of my feature is about 19,000. But it turns out there isn't a performance difference if you reduce it down to 3,000. So like once it hit like 2,500, then there's a performance difference. But up to 3,000, like there isn't a performance difference. And I have a visual for it in my notebook. You guys can look at it later. And just having a lower dimension of data allowed you to, research the best parameter faster. And lastly, I want to just give a huge shout out to Neurotech X and DS3, because I remember at the beginning, I didn't even know like how to use pandas well, like how to use pandas with Python. And I didn't know how to create visuals with Matplotlib. But by the end of like the entire competition, I really grow and learn a lot in terms of programming as well as general knowledge about neuroscience. And I know these opportunities will never come if I didn't participate in this competition. And lastly, I want to shout out to Jiling for answering all my questions on Discord, and hope you guys all have a nice day.
Woo! Thanks, Michael. That was a really nice presentation. We're super happy that we can share with you this certificate and for your active participation in this competition as well. We really learned a lot from you as well, and hope you can also participate next year and try to make this competition fun as well for next year. Great, so that's all we have for today. I want to thank you all for coming here to join us for this awesome ceremony today. And we want to hear what you liked and what you didn't like about this competition. So if you could provide us your feedback, down here is the link for the feedback form. And in order to incentivize, we have a $5 raffle giveaway. So if you were able to come to any of our events or were able to sort of consider doing this this competition, we'd love to hear what we could do better for next year and how we can improve. So I'll put the link in the chat. And I'll also share some links so you can also join us on Discord and things like that. And then finally, I have a sign-in link, and we'd love for you guys to sign in and let us know you were here today. Yeah, and with that, I guess if there's any questions or anything we want to talk about with any of the winners, their tactics, if anyone has anything you want to share, we can stick around for a little bit. But yeah, that will wrap up this year's first UCSD Neural Dataset Competition. So yay! Congratulations, everyone.
Yeah, thanks everyone for participating. It's our first time obviously putting this together, so we'll definitely have to put events like this together in the future as well. So yeah, couldn't have done it without you guys participating as well.